Hello, my name is Carlo Giacometti. I will talk about neural networks for audio. As the title says, I will show some easy example applications of neural network applied to audio classification problems. So the main topics I will talk about is, first of all, feature extraction, various declinations of that, and then I will have some small example applications, and these are all things that I was able to train very quickly on my machine. So it's kind of some toy examples regarding neural networks and audio. So as we said, feature extraction, this is very important. So this is one audio object in Mathematica. Sorry? Is this enough? Okay. So this is just a simple recording.
Right then. Perfect timing.
But what is underneath this? It's a bunch of numbers. In this case, we have a list of samples that's about 100,000 samples. One problem is that the length is variable. Here I am just grabbing the whole collection of example data that we have. As you can see, there is a huge variety of lengths in this case. It is quite a big amount of data. So the first step that we can take to bring this kind of data in a more reasonable format is partition the signal. As you can see, this kind of looks like an image would look like. The problem is that this first dimension is still variable. It depends on how much you recorded. And the partitions are very sensitive to the beginning point that you choose. So they are very sensitive to phase variation. The first step we can take is apply a Fourier transform on each partition to minimize the sensitivity of the phase. So this is what I'm doing here. I'm mapping the Fourier transform and taking, in this case, the absolute value. Usually the phase information is not crucial for many classification tasks, so we just discard that. And this is something that many of you might have seen already. This is a spectrogram. On this axis, we see the time, and on this axis, we see the frequency. And this is much more stable to phase variation. So if I move the endpoint of my partitions, what I see in the Fourier transform is fairly stable. We haven't reduced the dimension of the input that much, though. So what we can do is remap this spectrogram onto a nonlinear scale. In this case, I am using the Mel scale, which kind of mimics human perception of frequency. We perceive mostly logarithmically. So the operation involves filtering the spectrogram with a bunch of filters whose center frequencies are spaced according to this Mel scale. In this case, I am choosing 60 filters. I am applying this operation onto it. As you can see, we went very much down in dimensionality of the problem. This is still reasonably invariant to phase shifts, and kind of mimics human perception. And as you can see, this looks fairly similar to what we saw in the previous slide. The further step is to reduce dimensionality even more. A common strategy is to apply a discrete cosine transform to the Mel spectrogram and discard all the higher order components. This according to the assumption that most of the information lives in the lower order components of the Mel frequency septal coefficients. And here we go. This is much less intuitive. What this axis represents is not immediately obvious, but it retains most of the information, especially for signals like speech recordings. As you can see, we went from 100,000 elements to a matrix of 400 by 13 elements. So this is a good result in dimensionality reduction. We still have the problem of variable length, though. We didn't tackle that at all. So why do we care about this? We do have neural networks that can deal with signals of variable length, like some example layers from those are the basic recurrent layer, the long short-term memory layer, etc., etc. But we know that convolutional nets can be very effective and extremely lightweight in terms of training times and computation effort. So we would like to leverage all the knowledge that we have from image processing and neural networks. So what we can do is partition again our signal into fixed size windows, say 1 second windows, and then map a convolutional network onto each partition. So this is what we could have, for example, from the original signal. You see I have a list of images in the end that have all the same dimensions. The only variable thing is the length of this list. But we don't care too much about that because we are simply mapping the same network on all elements of this list. So this is captures, I think, most of the aspects of feature extraction that are relevant for audio neural networks. So some examples. The first example I want to show is digit recognition. I'm sure you are all familiar with the MNIST example for images. We have a data set of images. Each is a handwritten digit from 0 to 9. Here we have essentially the same thing, only we have recordings. Wow, evidently we are not happy playing this.
7, 5.
Well, playback is not working very well. But per each class, and as you can see we have digits from 0 to 9, we have a corresponding recording. A disclaimer is that this data set is an open source data set, so the amount of data is small. There are only 3 speakers, so we cannot expect whatever result we get to generalize well. So first of all, what kind of feature extraction are we planning to apply onto this data? We are planning to do MFCC extraction. We have a fixed duration of 1 second, and we use we will use only the 20 first coefficients resulting from this computation. One thing that is crucial is that we will need to do some data augmentation given the very tiny size of this data set. So for each recording, whenever we feed it to the neural network for training, we will randomly shift the signal by a time shift that will have a maximum of 0.25 seconds. So an important note, everything I will show today will use this audio utilities get feature batch function. This is something we have been developing, and it was ready just before the conference. But in 11.3, we will bundle this functionality onto a net encoder of audio that will take care of all this without the user having to worry about how to generate examples. So all of this kind of sketchy phase of feature extraction will be taken care automatically in net encoder. So let's look at what kind of features we are computing. Here I'm getting 4 examples. As you can see, the dimensions per each example are fairly tiny, 20 by 31 matrix. And they look like this. So it's a fairly small problem. The network that we will be looking at is very similar actually to the LeNet network. So it's just a couple of convolutional layers with pooling at the end, and then a couple of linear layers for classification. So let's look at this. The training will be, so as I said, I am using this internal function currently. This will get substituted by a net encoder of audio directly in the network definition. As you can see, the training can go quite fast, despite we are talking about audio files that live on the hard drive. And we are doing the feature extraction online, so the features are not pre-computed. I will actually stop the training and import a pre-trained network. I think the total training time was not more than 10 minutes, though, so it is definitely something you can play on your machines with. And we can look at the results on the training data. Of course, we get very good results. But we get similar results in terms of accuracy also on the test data. We get about 90% of accuracy, which is a fairly good result. One way to test it is I could record a digit spoken on with my voice and see if the net does something sensible. As I said, the network has been trained only on 3 speakers, so I wouldn't expect it to generalize too well, but it's still worth trying. 5. Let's see if it worked. Yep. And it actually gives a good result. Shadi tried this yesterday. It didn't work because there is no female voice in the training data. So data is the most important thing in these situations. The second example is about classifying cats and dogs, because of course, who doesn't want to look or listen at cats and dogs? So a cat, a dog. As you can imagine, the class, so the variables here are named cat classes, cat everything. I prefer cats. So the classes are easy. It's just cat or dog. It's a binary classification task. Here, we are looking at the MEL spectrogram rather than MFCC. We want to capture a bit more information than just 20 MFCC coefficients. Here we are using 60 filters to compute the MEL spectrogram, as you can see, and a fixed duration of 0.9 seconds. And these are some examples of the features that will be computed on our data. This is a slightly more big network. It's just the convolution layers have a smaller filter size, and there are more of them. The end result is kind of similar. And at the end, we still have the usual linear layers for classification purposes. The training is a bit slower here. I will not demonstrate, but this also took no more than half an hour to try and get reasonable results on my machine. I will import the pre-trained network. And let's look at the classifier measurements. Good accuracy on training data. Not as good accuracy on test data, but still not insanely bad. So what I want to do here is I take out the last layer of the network. So I will get a vector of length 2 per each input example. And what I want to do is a visualization of this length 2 vector to see if we actually can separate in a 2-dimensional space cats and dogs. Let's see. I am grabbing a random sample of 30 examples from the training data. The color is the proper label, and we can see 2 different clusters of, let's see what this is. I would say cat and dogs. And as you can see, we can achieve a very nice separation in the feature space. So the next example is instrument recognition. Here the data set is a bigger one and a more reliably constructed one than the other 2 that I showed. And in this case, we have excerpts from songs. And the labels is the predominant instrument in that clip, in that 2-second clip. We have various classes. Sorry for the abbreviation. It's something like cello, clarinet, flute, acoustic guitar, electric guitar, etc., etc. Here we want to keep even more information with respect to what we did before. So we are computing a MEL spectrogram, but with 128 filters. We want to keep a very good frequency resolution to gather information about the instruments. And also here we are working on a fixed duration of 1 second. And there is still a data augmentation part that randomly shifts the signal. So hopefully it will generalize, it will help to generalize well. The dimensions are slightly bigger, 41 by 128. As I said, 128 is the size, the number of filters that we are using in the MEL spectrogram. And these are what some of them look like. Well, let's see if we can get a slightly nicer example. Okay, so this one, for example, has we can see a clear harmonic structure into this one. And this is what our neural network will be exposed to. The network here is essentially equivalent to the cats and dog classifier. So a bunch of convolutional layers with a small filter size, and we increase as the depth of the network increases, we symmetrically increase the width of the network. And at the end, we have the usual pooling and linear layers to do some classification. Again, I will skip the training part and import the pre-trained net. And here I pre-computed the measurements actually because the amount of data is fairly sizable and the network takes a little bit to evaluate. So you get 85% accuracy on the training data and a similar result on the test data. So it seems to generalize quite well. It didn't learn example by example. We are still ignoring the time dependence of the problem. Per each sample, we are extracting one second segment. So what can we do to take this time dependence into account? So first of all, we can generate the full MEL spectrogram of the signal. So this will have a variable length. And then we partition this into 1 second partitions. So what we have is now a sequence of 1 second long partitions. And then, as I mentioned in the feature extraction part, we can actually map the network that we have already trained onto each partition. So this is one example of the feature we will be looking at. So there is a list of fixed size images that corresponds to one single label. So this is a voice sample, and this is the time evolution of this voice sample. Same here for a flute. I get a list of that shows the evolution as a function of time of the signal. So we can take the network that we trained before and chop off the net decoder that was doing the classification. So what we end up having is a network that takes a fixed size two-dimensional vector, well, three-dimensional if we take channels into consideration, and outputs a vector of length 11. And what we can do is map this network onto this list of images or 2D matrices. So if we only apply it onto one of these features, we get, as I said, a list of length 11. But what we want to do is actually map onto a sequence of two-dimensional matrices. So what I did here is visualize this. I am doing this operation on many examples. Each row is, in each row there are 10 examples that correspond to a single label. The horizontal axis will tell you which class the network is classifying to, and the vertical axis is time. So if we see a single straight line, let me see if I can increase the size of this, hopefully. So it will be slightly more clear. Okay, if we see a single vertical line, this network is fairly sure from the beginning to the end of the signal, it belongs to this class. But we have several situations where, sure, it starts in one class, but then the situation is kind of not obvious, and then it gets misclassified as a different one. So how can we improve onto this situation? We could, given this is simply a sequence of length 11 vectors, we could apply a recurrent network onto this input here. So this is what I have here. I map our chopped net onto the input, and then I have a bunch of long short-term memory layers, sequence last layer to get only one label from this sequence, and then some linear layer for classification. Also here, I will import a pre-trained net. This actually took quite a bit of time to train. And as you can see, we improved the results quite dramatically. This could be trained more. The training didn't flatten out on my machine. I just essentially ran out of time. So I can see this getting better results. So by taking into account the time dependence of the signal, we managed to squeeze some more accuracy out of the pre-trained net that was acting on fixed size partitions of the signal. My last example is acoustic scene classification. This is a very complicated problem. The idea is that you put a microphone into an environment, say a street or a restaurant or a park or something like that. Record whatever is coming to it. And then you need to classify what environment you are looking at. So there are I will show two examples here. Probably not very loud. Definitely not very loud. This is supposed to be a tram. This is supposed to be inside a car. Okay, so these are fairly boring examples, but I guess they give the idea. And we have a bunch of classes that are present in this data set. Also here we are doing a fixed size partition of 1.4 seconds, and we are still computing a MEL spectrogram. This time with less precision, we are only considering 40 filters. Hopefully that will be enough to capture information about the acoustic scene. And the big problem, the main reason why this is difficult to do with traditional signal processing techniques is that you can have a huge variety of sounds that happen in a specific scene that translates to a huge variety of actually shapes that you can see in a spectrum. So this is an extremely complicated classification in terms of classical signal processing. I will still use a very simple network. This is, again, if you go back to the first example of the digit classification, this is the same one. So a couple of convolutional layers and then some linear ones for classification. Again, I will cheat and import the pre-trained network. This one actually took quite a bit of time to get some results. And the accuracy of this network on the training test and on the training set is very high. 96% is an extremely high result. But if you look at the test set, as you can see, this network didn't generalize very well. There are a lot of misclassified examples here. They are not unreasonable. I mean, one of the biggest misclassifications is this one, and it's a cafe or restaurant misclassified as grocery store. So you could argue those are fairly similar environments, or a library misclassified as an office. So these are fairly understandable mistakes. So what are the solutions for this? Well, I guess just a more varied data set and possibly a bigger dropout to increase the generalization of the network and reduce the accuracy on the training set. Another operation that can be done is what we did in the previous example to take into account the evolution of the time evolution of an acoustic scene. So adding a bunch of recurrent layers on top of this convolutional net that acts on fixed size partitions. Okay, this was the last example. This is the team that has been working on audio. And of course, most of this is possible thanks to the neural networks framework, so they are not in this slide. There are too many people, but this is the team that has been working on audio processing. Thank you.